Before we get going, I want to do a little bit of philosophizing about how it is we learn things in physics. At the beginning of the week, we started with the Boltzmann model of vibrations in solids, and then we decided that that wasn't quite right, so we had to improve it with the Einstein model of the solid, and that was pretty good, but it didn't get the low temperature behavior right, so we had to improve it with the Debye theory of solids, and that was even better, but we're going to have to improve it later on in the year as well. And a perfectly valid question is, why didn't we learn the right thing at the beginning and not have to go through all of these models which are all wrong? And it's not just because I like telling, history stories about how all of this was developed, but the reason we do this is because this is always how we learn things in physics. You always learn the simple model, even though it's incorrect, first, because it's a lot easier to think about. So for example, you learn classical mechanics first, and it's not really right because there's special relativity and there's quantum mechanics, and you layer those on top later, but your intuition always falls back to the simple model that's a lot easier to think about, and that's why we do this. And this is exactly what we're going to be doing today when we talk about metals. We started last time, metals. And the simple, crude model we use for many, many things is the Drude picture of electrons in metals, which is basically just kinetic theory for electrons. And at the end of last time, we derived the Drude transport equation, d momentum dt equals the force on the electron minus p over some phenomenological scattering time, tau, where the force is the Lorentz force, the general force that the electron feels. So it's basically just Newton's equation with an added drag force, p over tau, which sort of represents scattering and sort of slows the electron down in some way. Now, for many experiments we're going to be interested in, we are actually doing some sort of steady state experiment. You might apply a steady electric field, you might apply a steady current, and you're interested in a steady state result. So it simplifies things a lot to look for steady states. So dp dt equals 0. So let's try to solve that. So dp dt equals 0. We'll put in the force on the right-hand side here. So the force, I'm going to replace that by the Lorentz force, plus v cross b. And then we need p over tau over here, but I'm going to replace p by mv over tau, just because we have a velocity here. Draw this the same. Velocity here, we'll put another velocity there. Now, velocity is a perfectly good quantity, but it's not actually what you are likely to measure in an experiment. What you're much more likely to measure in an experiment is the current density. Current density, very closely related to velocity. J is the number of the density of electrons. Density of electrons times the charge on the electron, which is minus e, times his velocity. Okay? So the current density is just how many electrons you have, with the charge they have, and how fast they're moving. So every time I have velocity in that equation, I'm going to plug in j instead and divide by an n and a minus e. And in one step, I'm also going to move e over to the other side and get this equation. E equals 1 over ne j cross b, and then plus m over n e squared tau times j. Is that good? Happy with that? Too many steps at once? Yeah? So I just plugged in j for v and then moved e to the other side and divided through by ne. Divided through by e. OK, good. So there's two terms in this equation, and we'll call them two different things. Let's call this E parallel, and we'll call this E Hall. Let me draw a diagram of this. So what we have is we have a block of metal like this. We're going to run a current through the metal like this. Current density in, current density out, like that. We might apply a magnetic field, maybe perpendicular to the metal like this, V. And then we will have E parallel in this direction, electric field in that direction, and then E Hall perpendicular to the current and perpendicular to the magnetic field as well, E Hall. And It's called the Hall electric field because it was discovered by Edwin Hall, who was doing exactly these kind of experiments in 1879. And he discovered that when he ran a current through a metal in a magnetic field, he ended up with an electric field perpendicular to both of them. You may have run into this before. It's a pretty clear result of the Lorentz force. What's happening is you're running electrons through the material, and they're trying to curve because of the magnetic field, and that builds up an electric field. Good? Everyone happy with that, more or less? OK. So let's try to think about this equation a little more closely. Let's take a simple case. Case 1, magnetic field equals 0. So in that case, we just have electric field. Let me turn it around the other way, move the j to the other side. So j, the current, is then n e squared tau over m times the electric field. This quantity here is a conductivity. Sigma equals conductivity. And it's a conductivity because it relates the electric field to the current. Now, the expression for the conductivity that we derived, n e squared tau over m, is the Drude conductivity. It's the conductivity we would calculate in the Drude theory. We just calculated it. And we should have pretty easy intuition for what's going on here. The conductivity has a factor of density up top because the more electrons you have, the more current you're going to get, and the more conductivity you're going to get. It has a factor of tau up top because longer tau, bigger tau, means longer scattering time. And the longer scattering time you have, or the less things you have to run into, the better your conductivity is going to be. Now, the factor of mass downstairs looks a little bit more complicated, but actually it just comes from F equals ma. If your mass is small, for a fixed force, your acceleration has to be larger. So you apply some fixed force, the electrons move faster if their mass were smaller. That's why the mass comes out downstairs. Now, we might ask, or Paul Drude might ask, is this a good answer or is this a bad answer? And right now, we actually don't know because tau is some unknown number. It's some phenomenon. He doesn't know how to calculate it. We have to put it in phenomenologically, so really it would fit pretty much anything at this point. So you might think of it, sort of turn this on its head, that measurement of conductivity is actually a measurement of the parameter tau. Okay? And that's frequently how it's viewed. All right. Now let's do something a little bit more complicated. Case 2. Case 2, which is b not equal to 0. And there are various ways we might think about b not equal to 0. One possibility of doing this experiment is we might imagine, suppose we know, so let's call this 2a. Suppose we know a couple things. Suppose we know the density of our electrons. Of course, we know the charge on the electron. Suppose we know the current. And we measure E Hall. Then according to Drude theory, we then get magnetic field, B. And in fact, this is a very frequently used method for measuring magnetic fields. It's known as a Hall sensor. And it's still used frequently in modern technology. Now let's be a little bit more detailed about this over here. Generally, if you have a current in a magnetic field, you will get something of the form, we define this quantity, RH B cross J. Notice that I turned the order of J and B over there to over here. This is just a definition of a commonly used quantity known as the Hall coefficient. So, if you know what J is, you know what B is, you measure E, you get the Hall coefficient, for example. So in Drude theory, comparing to that equation, so this is E Hall, sorry, E Hall. In Drude theory, comparing to that equation over there, the Hall coefficient, RH, is 1 over density times minus E. The minus sign comes from the fact that I flipped the order of these two compared to over there. So the Hall electric field that you would measure would be proportional to the Hall coefficient here. And if you're trying to build a Hall sensor in order to find accurate ways of measuring magnetic fields, using electronics or using voltage measurements, you really want the Hall voltage to be large as possible, so that you have a large electric field to measure. So to do that, what you do is you usually choose a material with a small density. So use small density to get big E. And typical Hall sensors are built with semiconductors and other materials that have a small electron density, and we'll come to semiconductors later on in the term. Now, let's turn this experiment now on its head, probably the way that Paul Drude thought about it. In his case, he probably knew, and so in his case, he probably knew the magnetic field, the electron charge, and the current. Measure E Hall, and what you get is the density of electrons in your sample, because of course he didn't know the density of electrons in his materials. Well, so let's try this. Suppose we do this for a bunch of different materials. So we'll take a bunch of metals like lithium, sodium, potassium, copper, sort of typical good metals. And the first thing that Paul Drude would have noticed is that for all of these metals, RH is less than 0, which is what he predicted by his formula over here. So that much is good. And then he can actually put in, measure the magnitude of E Hall and try to extract the density of electrons. And what he would have gotten was about 0.8 electrons per atom here, about 1.2 electrons per atom here, about 1.1 electrons per atom, 1.5 electrons per atom. Seems like reasonable numbers, a couple of electrons, one electron per atom, more or less. Is this a good answer or is this a bad answer? Well, if you think about it for a second, you'll remember your periodic table. Copper is the 29th element on the periodic table. So it has 29 protons and 29 electrons. And we measured 1.5 electrons per atom. Where'd the other 27.5 go? So this might have been a little bit puzzling to Drude. But actually, now that we know a little bit about the atomic structure, we know about the shell structure of atoms, we know a little bit about chemical bonding. We'll even talk a little bit about chemical bonding later on in the year. And we know that, in fact, many of the electrons in an atom are actually in orbitals very close to the nucleus. These core orbital electrons are basically stuck. So core orbitals, core orbital electrons don't move. The only ones that do move, outer shell electrons, also known as valence electrons, move. So the electrons that are running around in the solid are the so-called valence electrons. And from chemistry, we actually know how many valence electrons these materials have. And in fact, all these four materials have valence 1, meaning only one electron in the outermost shell. So if we assume only the outermost electrons move, the ones in the outermost shell, we should predict 1 electron per atom. And that's actually in fairly good agreement with what is measured experimentally. So that's pretty good for Drude theory. We get roughly 1 electron per atom moving around. So we might, emboldened by our success, we might try some other materials. So let's try some with valence 2. Valence equals 2. We have materials like beryllium. We have magnesium. Both of them have valence 2. And all of a sudden, we have a big problem. The big problem is that RH, the Hall coefficient, is now greater than 0. And this is completely puzzling from this picture of Drude, because Drude says that it should be just the density times the charge of the electron, which is negative. And so there's no way in Drude theory we're going to get a Hall coefficient which is positive. And this must have puzzled Paul Drude terribly. And later on in the year, when we study band structure of materials, we'll understand why this is. But it kind of looks like one of two things is going on. Possibility 1 is that the density of electrons has gone negative for some reason, if that makes any sense. Possibility 2 is that the charge carrier, the thing that's moving around carrying the charge, is not the electron, but something else with a positive charge. Neither of those seem to make much sense right now, but they'll make a little bit more sense later on, hopefully. But, you know, Drude was a very brave person, and he decided that we're going to ignore these two materials that don't seem to fit, the materials with valence 2 that have Hall coefficient positive, and we're going to go ahead and try to calculate some other quantities that kinetic theory or Drude theory should be able to predict. Now, you studied kinetic theory last year, and one of the things that you were able to calculate in kinetic theory was thermal conductivity. I'm not going to go through the whole calculation because it's something that you probably learned very well last year. It's probably not worth going through again. But I'll write down the answer that you probably, well, it should probably look familiar. The thermal conductivity for a monatomic gas is 1/3 the density of particles, heat capacity per particle. This is CV over N. And then there's a velocity and a scattering length, which is a velocity times the scattering time. And in kinetic theory, we can take the velocity to be square root of 8 kBt over pi times the mass. Does this all look familiar? Is this vaguely familiar from last year? Hopefully. OK. So what we do is we actually just plug this in. It's going to be v squared, because v occurs in two places. We'll plug in the expression from kinetic theory. CV over N is 3/2 kb from classical gas physics. And what we get is the thermal conductivity is 4 over pi. So let's see. So the pi comes from down here, having gotten squared. I guess we got a 2 over there, which canceled the 8 to make a 4. Then we have n tau kb squared t over m. So that's the prediction for the thermal conductivity in Drude theory. Now, again, we have this question, is this a good answer or is this a bad answer? And we don't really know because we have this tau, this unknown quantity tau, in this equation. But it's not so bad because we also had sigma is ne squared tau over m. And we can look at the ratio of these two quantities and get rid of tau. So let's do that. We'll take what is known as L, the Lorentz number. This is not actually the same guy who is Lorentz transformations and Lorentz force. This is Lorenz without the T in his name. Lorentz number. Everyone seems to have the same name in Germany in the 1800s. So we can take the ratio of the thermal conductivity to T times sigma here. The taus cancel, and we're left with just 4 over pi and kb over e squared. That's it. And this result, well, if you put in numbers, you discover it's 1 times 10 to the minus 8 watt-ohms per Kelvin squared. And this result is kind of interesting because it's what we call universal. It doesn't depend on temperature. It doesn't depend on the mass of the electron. It doesn't depend on the scattering time of the electron. It doesn't depend on the density of electrons. It doesn't depend on anything except these fundamental quantities, Boltzmann's constant and the charge of the electron. It's kind of an interesting prediction. And in fact, the fact that the Lorentz number is fixed, L the same for all materials, was known, and all T, this is known as the Wiedemann-Franz law, Wiedemann-Franz, and it was known since the mid-1800s, and no one had the foggiest idea why it was true. They just measured it. Wiedemann and Franz were Germans who liked to measure things like thermal conductivity and electrical conductivity in the middle of the 1800s. And they noticed that if you take this ratio, it comes out pretty much the same for all materials. I guess if we want to be precise about it, in fact, for lithium, it comes out about 2.2 watt times 10 to the minus 8 watt-ohms per Kelvin squared. For copper, it's about 2.0. For iron, it's about 2.6. So it's pretty close to Drude's prediction. OK, it's off by a factor of 2. But at least it's in the right ballpark. It's a very crude theory. And before Drude, no one had any idea why this ratio should be fixed for all materials at all. So this was really a great step forward. And the intuition that we should have in our heads is actually not that complicated. The intuition should be that whether we're thinking about heat transport or whether we're thinking about electrical transport, we're really just thinking about electrons moving. If we're thinking about regular conductivity, we're sort of counting how many electrons move, and each electron has a certain amount of charge on it. Whereas if we're thinking about thermal conductivity, we're still counting how many electrons are moving, but each electron is moving a certain amount of heat, which is proportional to the temperature. So that ratio of thermal conductivity divided by temperature, then divided by regular conductivity, should come out roughly constant, because in all cases, you're just counting the number of electrons that move. OK, so this was a really good result from Drude, explaining the Wiedemann-Franz law. But there's a really big puzzle. And the puzzle is that we used rather glibly the statement that CV over N is 3/2 kB, which is a perfectly good result for a monatomic gas, but it's just not true for electrons in a metal. Not true for electrons in metal. Why not? Well, we measured it and we saw it's not true. Remember, in metals, the heat capacity is alpha T cubed, and we identified this alpha as being vibrations, or Debye theory, plus gamma times T. And in fact, this gamma times T is special for metals, so this is the heat capacity of the electrons running around in the metal. And for any reasonable temperature, gamma times T is much, much less than 3/2 kB, as long as T is not ginormous. Ginormous. That means huge. Like 10,000 Kelvin. As long as T is not 10,000 Kelvin, gamma T is much less than 3/2 kB. So somehow or other, even though we used this thing that was clearly incorrect, we gave the electrons a heat capacity of 3/2 kB each, whereas in fact, if you measure the heat capacity of the metal, that heat capacity is just not there. The only heat capacity the electrons have is this gamma times T, which is much, much less than 3/2 kB. So how did we get this right? What's going on here? Well, the problem here actually becomes much, much more obvious if we look at some other quantities. Let's look at thermoelectric properties. Thermoelectric properties. Electric properties. This is the kind of experiment we want to look at. Here's a block of metal. We want to run a current. So here's a current source. We run the current through the metal. So the current drags electrons through the metal this way. And then because the current is moving through the metal, it means the electrons are moving through the metal. And therefore, heat is all. Oops, I should have the electrons moving this way. Current moves in the opposite direction. Let's put the electrons moving this way. So then the heat current gets dragged in the same direction, because each electron is dragging a certain amount of heat with it. So one can define JQ. JQ is now the heat current density. Heat current density. JQ is equal to some coefficient pi times the regular current density, J, and pi is known as the Peltier coefficient. Peltier coefficient. And this is known as the Peltier effect, after Mr. Peltier, who discovered this effect in 1834. Another one of these people from the 1800s who liked to measure thermal and electrical transport. Anyway, actually, I should comment here as a bit of an aside that Peltier effect is actually a very technologically useful effect to know about. You can actually build a very nice refrigerator with it, which has no moving parts. The idea is that if you want to move heat from one side, the inside of your refrigerator, to the outside of the refrigerator, to move heat out, you just run current, and it drags heat with it, and leaving this side cold, making that side hot. In fact, you can buy refrigerators that are built like this. They don't have pumps and things like that. They're not loud. They're very quiet. Frequently, they're actually used as wine refrigerators. I don't know why, but you can buy a Peltier refrigerator on the open market these days. But one thing that one has to keep in mind in a Peltier refrigerator is that you can't just keep running more and more current and getting it colder and colder, because at some point there's going to be an I squared R heat dissipation. So you'll be dissipating power, and if I squared R gets too big, then you start heating things up. So for small currents, this side will get cold, this side will get hot, but for large currents, everything gets hot. So the art form in building a good Peltier refrigerator is that you have to find a material with a large Peltier coefficient but a small resistivity. And there's many, many people whose job it is to find these materials. All right, anyway, we're going to try to calculate this Peltier coefficient. How do we do that? Well, the heat current density, JQ, and we have the electrical current density. Well, we know what the electrical current density is. It's the velocity the electrons are moving, the density of the electrons, and the charge on the electrons. The heat current density, very similar. It's the velocity, well, it's a factor of 1/3 if you're honest about it. That's this usual geometric factor. Don't worry about it too much. The velocity the electrons are moving, the density of the electrons, and the heat that each electron is carrying, which is CVT. If we take the ratio of these two things, we'll get a Peltier coefficient. Pi is CVT over 3 times minus E. If we plug in the usual kinetic theory result of CV is 3/2 kb, which I'm already warning you is not a good idea, we end up getting kb over 2 times minus E times T. And frequently what people do is they actually consider the ratio known as S, which is pi over T. S is known as the Seebeck coefficient. Seebeck was another person from the 1800s who liked to measure electrical and thermal properties. I believe he was from Estonia, actually, for anyone who happens to be Estonian. Anyway, so if you take that ratio, we just get the universal constant kb over 2 times minus E, which has a numerical value of minus 0.4 times 10 to the minus 4 volts per Kelvin. And the problem is here that if you actually measure the Seebeck coefficient for any metal, you discover actually S is 100 times smaller. So this is an obvious, much more obvious error in kinetic theory. Kinetic theory is going way wrong, and the source of this problem is that we're using this heat capacity for the electrons that is just wrong. And the problem comes from why? Why the problem? Why the problem? Because, in fact, C over N is much, much less than 3/2 kb, or CV over N is much, much less than 3/2 kb. Well, if this is true, if we're using this heat capacity that's so wrong, why is it that we did OK when we calculated way up there, when we calculated the thermal conductivity? We got the ratio of the thermal conductivity to the regular conductivity. We got the Lorentz number almost exactly right, whereas the Seebeck coefficient is completely wrong. So something's inconsistent. Somehow or other, the Wiedemann-Franz law is coming out right. The Seebeck coefficient is coming out completely wrong. And the reason that this happens, the reason we got the Wiedemann-Franz law right, reason why kappa is right, is because we made two canceling errors. Two canceling errors. The first one I've mentioned already, that CV over N is much, much less than 3/2 kb, and we use kb. But there's another one. We also used v squared, expectation of v. We plugged in the kinetic theory result, 8 kBt over pi m. And in actuality, v squared is actually much, much greater than 8 kb over pi m. And these errors in the thermal conductivity, they almost exactly cancel, so we get the thermal conductivity almost exactly right, whereas this quantity, v squared, doesn't enter in the Seebeck coefficient, so we get it completely wrong because we use this but not this. Okay? Now, the first chance of the year to win fabulous prizes, one very high quality chocolate bar. Actually, my favorite chocolate bar was sold out, so this is a slightly less than a very high quality chocolate bar. So, if anyone who can tell me why we made both of these mistakes. What did we do wrong? What did we leave out? Come on, come on, come on, come on, come on, come on. What did we forget? Someone? Yes.
Was it using the expectation value of v times by itself instead of the expectation value of v squared?
Okay, so I'm not going to give you the chocolate bar for that, but it's a good idea. Generally, using expectation of v versus expectation of v squared will make an error, but it's usually only a factor of 2 kind of error, so it's a small error. So there's various debates as to which one is better to use in this case, but I agree that that's a potential problem. Anyone else? Yes? Yes, that's it. Fermions, yes. So I would throw this to you, but it would probably miss, so you can come down and get it afterwards. So the thing we left out was Pauli exclusion principle. Electrons are fermions. You can't put all the electrons in the same state. They're not a classical gas in any sense. They're a Fermi gas. And so we're going to have to treat that properly. Maybe I'll write that down because it's really important. Fermi statistics. Fermi statistics. So we have to deal with that. And that's what we're going to do next. But before doing that, I'm going to do a little bit of a summary of Drude theory. Drude summary. So Drude summary, many things right. Many things right. Many transport properties you get right. And I think for homework, you'll study a couple of other things that you get right in Drude theory. It's still used very heavily. Drude theory is used very heavily for understanding metals and semiconductors, particularly good for semiconductors. But it has problems. And some of the problems are, well, RH can have wrong sign. We can have CV over N is actually much, much less than 3/2 kb, where we use 3/2 kb in the calculations. And you can get Seebeck wrong by 100, and so forth. In fact, you can get the sign of the Seebeck coefficient wrong as well, but being that we're off by in magnitude by a factor of 100, it seems a little bit superfluous to worry about the sign all of a sudden. Okay, anyway, so these are some of the summaries of Drude theory. But nonetheless, this was how people understood metals for the first time in the 1900s. Before Drude, people didn't understand metals at all, and still Drude theory is an extremely good way to roughly understand metals. But nothing really progressed for about 25 years, and Drude theory was all there was, and people didn't understand why these things didn't come out right. But around about 1925, there were a lot of sort of simultaneous, enormous advances in physics. 1925 was the Pauli exclusion principle. 1926 was the Schrödinger equation. Also 1926 was Fermi-Dirac statistics. And in 1927, someone came along, a guy named Arnold Sommerfeld, 1927 Sommerfeld. Sommerfeld was nominated for the Nobel Prize 81 times and never got it. Poor guy. But his idea was he was going to treat metals with Fermi statistics. Treat metals with Fermi statistics. In other words, we're going to account for the fact that the electrons are actually fermions. And so now we have to do a little bit of a review of what we know about Fermi statistics. And the most important thing we have to remember is the Fermi occupation function. NF of beta epsilon minus mu is 1 over e to the beta epsilon minus mu plus 1. Mu here is the chemical potential. And this NF thing, NF is the probability, the prob that an eigenstate, that an eig at energy epsilon is occupied. Good? Yes? Yes? Question? No? Yeah? Good? All right. Good. So let's plot this thing. So we have energy on this axis. We have NF on this axis. And somewhere over here, we have the chemical potential, mu. At 0 temperature, the Fermi function goes from 1 to 0 as a step function. That's supposed to be flat up there. So this is at t equals 0. It's a perfect step from 1 down to 0 at the chemical potential. At t not equal to 0, it's somewhat smoother. Looks like this. So this is t greater than 0. And the width over which it drops from 1 to 0, so this width here, is roughly kBt. Okay, does this look vaguely familiar from last year, I hope? Yeah. Okay, so now it's useful to have a couple of definitions that we're going to use. Definition: the chemical potential mu at t equals 0 is known as, is called the Fermi energy, EF, the Fermi energy. Fermi energy. You'll discover that a lot of things are named after Mr. Fermi. Okay. Now, I should warn you that there is some disagreement in the literature, in the books, as to what you're supposed to call the Fermi energy. Some people think that the chemical potential and the Fermi energy are actually synonymous. It's mean the same thing. Most people, I believe, think that the chemical potential at 0 temperature is the Fermi energy. And that's the definition we're going to work with. It's actually, it makes sense to do that because why would you just have two terms that mean exactly the same thing? You just call it the chemical potential if you mean chemical potential. Chemical potential at 0 temperature, we call it the Fermi energy. For electrons, which are free electron waves, we generally have h bar squared k squared over 2m is the energy, is an energy. If you have a wave with wave vector k, its energy will be h bar squared k squared over 2m. So if we fix this thing to be the Fermi energy, then we define kf to satisfy this equation. So kf is defined by this equation. This defines kf is the Fermi momentum. Fermi momentum. So if we know the Fermi energy, we just calculate from this equation what the Fermi momentum is. Okay? Everyone happy with that? All right. So if we have some physical system, we want to know how many electrons are in that physical system. We write n, the total number of electrons, is the sum over all eigenstates, eigs, of the Fermi occupation factor of beta epsilon of the eigenstate minus mu. So why do I write it like this? So this is the sum over all possible states in the system, the probability that that state will be occupied. And if you sum up over all eigenstates, you get the total number of particles in the system. Good? Yeah? You could also turn this on its head. If you know the number of particles in the system, you could use this equation to figure out what the chemical potential is, if you have to do that. Now, as we did in the Debye theory, we had to frequently sum over all possible plane waves. So one thing we should be familiar with at this time, I promised you we would use this a lot, is the sum over all possible plane waves gets replaced by an integral d3k over 2 pi cubed. So every eigenstate is a particular plane wave in our box. So the sum becomes an integral d3 cubed over 2 pi times a factor of the volume. The only thing that's different is I'm going to put a factor of 2 out front. And the factor of 2 is for spins. That electrons have two possible spins. In one particular plane wave, it can be either spin up or spin down, so two possible states. And then we're integrating the Fermi factor, beta epsilon of k minus mu. Okay? So far, so good? All right. So at low temperature, at low T, this thing here is a step function. This is step. Which the step function would tell us we should integrate the number 1 up until the energy is the Fermi energy. In other words, all the electrons are filled, all the states are filled below the Fermi energy, and everything above the Fermi energy is empty. So we can rewrite n is 2v, let's pull out the 2 pi cubed, integral d3k up to k less than kf. So saying that the absolute value of k is less than kf, the Fermi momentum, is equivalent to saying the energy must be less than the Fermi energy. Good? Yeah? Okay. Now, what this is telling us is that the filled states here, form a ball of radius kf. And the filled states at 0 temperature are usually known as the Fermi sea. Again, something named after Fermi. And the surface of the ball, surface, is known as the Fermi surface. So it's the sphere, and everywhere around the sphere, the surface of this ball, the energies are all EF. So if you have a sphere of radius KF, everything on the surface of that sphere has the same energy, and the energy is the Fermi energy. Good? All right. So last thing we have to do is we have to actually calculate the volume of that sphere, the volume of that ball. So we have 2v over 2 pi cubed, and the value of that integral is just going to give us the volume, which is 4/3 pi kf cubed. And then with a little bit of rearrangement, we can move the v over to this side, cancel some factors. We'll get n over v, which is the density, n, electron density, E density, which is kf cubed over 3 pi squared. Then solve this for kf. We'll get kf equals 3 pi squared times the density to the 1/3. So if we know the density of electrons, we know kf. And then we can plug kf back in to our equation, which I'm just about to scroll off the top to get EF. So EF is h bar squared kf squared over 2m equals h bar squared over 2m times 3 pi squared n to the 2/3. And this is a rather important equation. We're going to use it later on. So it tells us what is the Fermi energy in terms of the density. So, how big is the Fermi energy? Well, first we have to figure out what the density is. What density should we use? Well, let's try density of about 1 electron per atom, which seemed to work pretty well for Drude theory, at least for some of these metals. If we do that, say for copper, EX copper, we get EF is approximately 7 electron volts. And is that a big number or a small number? Well, it's useful to convert it to a temperature, which is known as the Fermi temperature. So I'll define Fermi temperature. Again, something named after Fermi, temp, which is TF equals EF over KB. And for copper, TF is about 80,000 Kelvin. Huge, 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 huge. So typical Fermi energies and Fermi temperatures in metals are absolutely enormous. And the reason for this is because there's a lot of electrons. You have 1 electron per atom. There's a lot of atoms. When you start putting electrons into your system, you fill up the low energy states first, the ones with the smallest k. But then those are filled, and you have to start filling up higher and higher and higher energy states. And by the time you put that last electron in, you've gotten up to an enormous energy because the density of these electrons is really, really big. So let's actually plot the Fermi function again. So here's NF, here's 1, here's EF, or the chemical potential, approximately 80,000 Kelvin, if I take out a KB. And the Fermi function will look like this. It drops in a very, very small range. This is KBT, T room. It's even more exaggerated than I've drawn. It's even narrower little drop than I've drawn, because this distance here as a temperature is 80,000 Kelvin versus our room temperature, which is 300 Kelvin. So this distance over which the Fermi function drops from 1 to 0 is a very, very narrow sliver at the top of the Fermi surface. And in fact, this picture here gives us already a hint as to why the heat capacity of the metal is so low, so much lower than we would have guessed. In order to have heat capacity, you have to be able to absorb some energy. So you imagine an electron in some eigenstate, it absorbs some energy, and it jumps up to a nearby eigenstate with a little more energy. Well, all of these electrons down here, they can't absorb any energy because all of the eigenstates near them are already filled. There's nowhere for them to go. They're completely frozen. They can't absorb any energy at all. The only things that can absorb energy are the things close to the Fermi surface where they can jump above the Fermi surface and absorb energy, because there's an empty state there for them to go into. If there's no empty state to go into, there's no way they can absorb any energy at all. So that gives us a hint as to why the heat capacity is so low. One final thing is we can look at the typical velocity, which is known as the Fermi velocity. Apparently, right? Okay. Vf, which would be h bar kf divided by the mass. It's k, kf. And if you put that in, you get a huge number. Huge equals huge. Approximately 1% of the speed of light, which might surprise you. Every metal that you ever run into contact with, things like copper, lead, silver, tungsten, whatever it is, it has electrons in it running around at speeds of 1% the speed of light or even greater. Now, that might sound surprising to you, and in fact, relativity starts to become important if you're doing things carefully at those speeds. But in fact, it's not surprising once you think about how many electrons there are. There are tons and tons and tons of electrons, one per every atom, or several per every atom in some cases. And so all the low energy states are completely filled, and you just have to keep building up to higher and higher and higher energy states. And the electrons on the top of the Fermi surface, on the Fermi surface and the outer edge of the Fermi ball are extraordinarily high, have extraordinarily high energy, high kinetic energy, therefore extraordinarily high velocity. And I guess we stop there, and I guess I see you Monday. Thank you.